Hello everyone, we are back and we are going to look at our Pset 2 solutions for fall 2021 for Engineering 45. Alright, so let's look at what the question is asking us to do. So for each, identify what type of conventional unit cell is present, number of atoms in each cell. So again, let's go ahead and start to kind of draw this out. So what type of conventional unit cell is present? So this is simple cubic, this is going to be FCC, and this is going to be BCC. So again, we've done that. Number of atoms, 1, 4, 2. Number of nearest neighbors, I have 6, 8, oh, excuse me, undo that. I have 12 and 8, so these are my number of nearest neighbors. The nearest neighbor distance, for all of these, it's always 2r. The lattice parameter, so A for simple cubic is equal to 2r. For FCC, A is equal to 2r root 2, and for BCC, A is equal to 4r divided by square root 3. The next nearest neighbor distance is also this, and then for simple cubic, it is 2r over square root 2. So we got that. Atomic packing factor, we know that for FCC it's 0.74, and it's less for the rest of these. And they're in the notes as well, so you need to give a quantitative answer. Any of these cells close packed, only FCC. What are the primitive cells? Only simple. So FCC is the close packed. All right, excellent. Determine the crystallographic directions. Are any directions close packed? What are the close packed directions for simple cubic? So close packed directions for simple cubic, 1, 1, 0, 0. For BCC, 1, 1, 1. For FCC, 1, 1, 0. So let's determine the directions, and then let's see if there are any of these directions that are close packed for simple cubic. So I'm going to go ahead and erase down, give us some room, and then we're just going to kind of scroll up here. Oops, I'm going to scroll down here. So let's go ahead. Actually, I could just scrape this up. All right, so let's go ahead and look at this vector here. So what's my finish? 0, 0, 1. What's my start? It is going to be 1, 0, 1. So that leaves me with 1 hat, 0, 0. So that's that direction. So that is a close packed direction. Let's look at this over here. I am going to do my finish. So that's going to be 1, 1, 0 minus my start, which is going to be 0, 1, and then 1 half. So when I do that, I'm going to be left with a 1 hat. I'm going to be left with, actually, excuse me. I'm going to undo that. I'm going to be left with a 1. I'm left with 0, and then 1 hat minus, which is going to end up being 2, 0, 1. So there we go there. What about this guy? Well, let's go ahead and let's draw this. Actually, I'm going to go do this one. I'm going to do this one next. So where's my finish? 1, 0, 0. Minus my start, which is what? 0, 1, 1. Leaves me with 1, 1 hat, 1 hat. There we go. And then finally this guy. So where's my finish? It's going to be 1 half, 0, 0. Minus my start, which is what? 1, and then, actually, let's see. It's going to be 1, and then it's going to be a half, 0. I'm going to assume that's half. So that leaves me with, so 1 half minus 1, so 1 half hat, and then 0, 0 minus 1 half, it's going to be another 1 half hat, and then 0. So that will be, end up being 1 hat, 1 hat, 0. There we go. So only those 1, 0, 0, really only this direction is close packed. All the rest are not. Fantastic. So, for B and C, identify the crystallographic planes. Be sure to indicate your origin. Select a new origin. Are any planes close packed? So close packed planes for simple cubic, none. BCC, none. FCC, only these ones. Let's go ahead and draw our direction or draw our planes. So here. So I'm crossing the origin here. So I'm going to start my new origin like this. So I'm only intersecting. So this is going to be 1, 0, 0. What about this guy? I could keep my origin. So where am I intersecting? I'm intersecting half, never. So that's going to be 2, 2, 0. I take my intercepts and then I reciprocal them. So again, my x-intercept is a half, half, and I flip those two. All right. I'm pretty sure that's all that answer there. Calculate the planar density for the quantitatively for the plane in B. All right. So for B, I have FCC. So I know that my FCC is 2r square root of 2. So I'm going to have a plane like this. Here, 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 here. So I know this is A, this is A. So my planar density equation, how many atoms? Quarter, 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 1. So I have 2 pi r squared over a squared. So let's go ahead and get that out. Pull out our old friend, handy friend, Mathematica. I don't want to be copyright infringed. So I will not. I don't know if that music is fair use or not. Alex Trebek. Anyways, so let's go ahead and say A is equal to 2 times 2r times square root of 2. And then my planar density is going to be pi to 2 pi times r squared divided by a squared. Pi over 4, and numerically 0.785. There you go. So that's my planar density quantitatively for that plane. All right, draw an FCC cell in D. So let's go ahead and draw that. I'm going to kind of erase a bit here. So I need an FCC cell. Again, it's not the more, a little bit more annoying one to deal with, but I'll draw it right now. And then I need atoms at the corners and atoms at all the faces. Anyways, a little bit ugly, but it's the best we can do. All right, draw an FCC here. Draw the 2 hat 1 direction. So I need to draw in the unit cell 2 hat 1 1 hat. Yep, 2 hat 1 hat direction. So if I'm going to draw this, I'm going to do my finish minus my start. So I know this is probably going to be a 1, so 0, and this is a 1, and then I have this as a basically a half. This is a 0, and I'm going to have this as a 0. I have this as a half. So if I do that, you'll see I'll get 1 hat, and then 1 half, and then 1 half hat. So multiply that out. 2 hat 1 hat. So I could do that. My finish is going to be 0 1 half. That's where my arrow finishes, and my start would be 1 0 1 half. So from here to here. Anyways, finish, start. And that's it. Oh, sure. Oh, excuse me. This is an X. My apologies. Over here. So that's my. Even I make mistakes occasionally. It's been known to happen. Only once. Only in this video. There's no other mistake I've ever made in my life. All right. Anyways, is this direction close packed? No, because it's not the 1 1 0 direction, so it's not close packed. Draw the 1 hat 0 plane. So I want to draw the plane. I need to go and actually find a coordinate where I can go back and to the left. So I'm going to start my origin here. So this is my new x, this is my new y. So I need to cross -1, I need to cross -1, and it's going to be like this. So if I choose my origin like this, again, this is my new x, so I cross my x at -1, new y at -1. There we go. So that's it. I should actually do that quite easily. So again, you can kind of do that right there, the 1 hat 0, depending on your origin. So I chose this is my new origin, and so now x -1, y -1. There we go. So I've got that. Calculate the planar density of this plane quantitatively. Is it close packed? So we know it is not close packed. It's not the 1 1 1, but we can calculate it quantitatively. So I'm going to have an atom here as well. So atoms at the corners. I know this distance is a. This distance is a root 2. So I have my planar distance going to be pi r squared divided by a times square root. So all I have to do, I can adjust this here. I can do a times square root of 2. And that's my planar density. Quite low. Pi r squared. So again, oh, excuse me, sorry about this. There's also an atom here and an atom here. So that makes much more sense. So you can see here, I'm crossing this plane like this, x, or actually, x here, minus 1, 1. So actually I'm crossing here and here. No atoms here, but along the face there. So it's actually 2. So that makes a little bit more sense. That number seemed a little bit low. There we go. That is our planar density. So we have done all of these, calculated. You've shown me doing a mistake again. But anyways, we get those values. Now, let's draw the directions in the unit cell below. So 1, 0, 1. Make sure I'm going to write those here. 1, 0, 1, 1, basically 1, 1 hat, 3, and then 2 hat, 2 hat. So let's go ahead and draw these. So 1, 0, 1. Again, I could kind of draw those. So let's go ahead and draw those directions. So just nice and slowly to kind of start us off. So I could go. Actually, I could just go here. That one's a pretty straightforward one because I could just go 1 and then no here and then up there. So that's my 1, 0, 1 for my value here. Finish minus start, right? So what I'm going to do is I'm going to do third and then 0. I'm going to do 0 and a third here, and then I'm going to do this as 1 and 0. So when I do that, I get a third, I get a third hat, and then I get 1. Multiplying that out, I'll get this. So my finish minus the start, so my finish is a third up here, and then 0 and then 1. So that's my finish, and then my start is going to be 0 and a third. So right here. So something like that. And then here, kind of the same principle. Finish minus my start. Again, I want 0, 1, 0. And I'm going to do this as 0, a half. And then this is a minus 2, so this is going to be a 0 and a 1. So when I do that, 1, I get a hat half, and then I get 1 hat. Multiplying that out, I'll get that distance. So finish is my 1, 0, 0. So that's my finish. And my start is, where are we at? 0, 1 hat, 1 half, and then 1. There we go. And that's it. So that is my directions. So now let's get into our planes. All right, so let's draw the planes in the empty unit cell below. So I've got 103 and 1, 2 minus 1. So 103, 103, and then let's also draw the 1, 2 hat 1. 1, 2 hat. So let's draw this 103 first. So again, my intercepts, x, is going to be equal to 1. And then my z-intercept is going to be basically a third, so right here. So I could draw my cell like this, a plane like this. There we go. That's it. Then I'm going to erase. Whenever I have a negative, I'm going to have to try to redefine my origin. So I want my negative, I think it's 1 to have 1. Yep. So my intercepts are x equals 1, y equals basically minus a half, and then my z equals 1. So I'm going to go ahead and I am going to draw my origin. Let's see. I'm going to draw my origin right here. So this is my new x, this is my new y, this is my z. So z of 1, my x of 1, my y of minus a half. I'm going to draw here, and it's going to go back up. There it is. So that's my new origin. There's my planes. Fantastic. And then I think, let's look at the PDF art. What material am I working with? What is the integral of first peak? What's the actual material? What element? Draw the PDF for metal, polymer, liquid. So PDF of metal, polymer, liquid. I don't even have to look at the problem. I can answer that. Metal, spikes on indefinitely. For liquid or polymer, they actually look exactly the same, except that usually polymers will have a little bit more kind of order. So you may see something like this for a polymer, and then like that. A liquid, they kind of look like this, where it kind of dies off a little bit sooner. And it needs my credentials. Windows, you're not getting my credentials. Anyways, so that's going to be a metal, that's going to be a polymer, and a liquid. So polymer and liquid look very the same. So the question is, what material is this? So I know it's a metal. I need to figure out what's the integral of this peak. So I know that this distance, 2.94, is equal to 2r. So my metallic radius, is going to be 2.94 divided by 2. So 1.47 is my metallic radii. So that's great. I also know that this distance here is going to be my next nearest neighbor distance. So for BCC, I know that this is equal to 4r divided by square root of 3. For simple cubic and for FCC, my next nearest neighbor distance are both 2r root 2. So let's plug in. We know our value for r, so what material is it, BCC or FCC? So let's go ahead and see. So I'm going to call this my, this. So I'm going to say that this is going to be my radius. I'm going to call it little r. I'm going to actually assign it a variable and not make it look weird. So 4 times r divided by square root of 3. 3.39, that's looking pretty good, but let's go ahead and double check it. So that's that. What about 2 times r times square root of 2? All right, so it is BCC. So I know that my integral gives me my number nearest neighbor, so that is 8. So now I just need to go look in my periodic table for a BCC structure with a metallic radius of 1.47. So I'm going to go and look and make sure that looking at my BCC structure, it is the one with the cross. So let's go ahead and look at some BCC materials. And my metallic radius is that, if we look over here, my metallic radius, because again, I'm looking at metal, it's going to be the second number from the top. So scroll down, scroll down, scroll down. I need to look at my BCC materials. So 1.47, 1.47. Wouldn't you know? Niobium. That will work. So that is our answer. That is, I believe, our problem set. So let's just double check and make sure we've answered everything. That's pretty much it. So look this over, and yeah, I will see you all next time. Thanks. Bye.